So one thing I can say about this problem, and one thing you will probably use a lot in your future mathematical endeavors, is the following fact. It's a very simple one, but it is very powerful. Precisely, it is the observation that e to the 2x is equal to e to the x to the 2. In this case, it is very specific. In more general cases, you could get something like this. Say e to the x, e to the 2x plus, let's say, 3e to the x plus 4. Let's say this is equal to 0. And you don't know what to do. Well, if you use this remark, then e to the 2x is e to the x squared plus 3 e to the x plus 4. And this is equal to 0. And then this is very nice because it's a polynomial, but it's not a polynomial in x, it's a polynomial in e to the x. So it's like I do x squared plus 3x plus 4. And if I'm solving this, then I would get that e to the x is equal to, well, if I factor this out first, I get what? I get e to the x plus 2, and then e to the x plus 1, right? You can check this yourself. Then in this case, e to the x is either equal to minus 2 or e to the x is equal to minus 1. And then you solve for x. For example, and I'm just giving an example. This has absolutely, okay, not absolutely, at least this construction has nothing to do with the fact that this integral is going to be some value. All I'm saying is that this piece of insight is very important. So people usually do not notice this, that e to the 2x is e to the x squared. This is very, very, very powerful. I just came up with an exercise where this might be useful. I don't think you'll see this exercise anywhere, where you have to deal with e to the x as like a polynomial in terms of it, and you try to solve it. This is very rare. Usually you have something like this, right? You have, this is more familiar. This is more familiar, but you could also have this. And this is kind of an eye-opener for you. This is one context where we can use this simple observation. And in this case, we will do this. So I'm just sharing with you some of my insight. This is really just hand waving. I came up with an exercise on the spot just to show you how this simple observation, seemingly simple observation, can get you very far. All right, e to the x, all right, e to the x squared, as we've agreed, minus e to the x dx. And then I have an inside function, right? I have an inside function, it's this one. Okay, and once I have an inside function, I immediately look at its derivative. So what is the derivative of e to the x? It's also e to the x. And now a question is, do we have e to the x in our expression? And the answer is that we do. Then definitely, with 100% probability, if you choose u to be the inner function and you take the derivative, and the derivative is in your expression, then you should proceed with integration by substitution. So let's do that. e to the x is u, so I'll just write u, and here I'll write u. Here I'll just write e to the x. Now notice that we still need to make dx the subject. In this case, dx will be du divided by e to the x. That's why I leave e to the x as it is. So I would replace this dx with du divided by e to the x. These will cancel out. We're happy. Everything's nice. Because we have integral with respect to du. We have u squared minus u. Here we have a 1. So it's good. It's going good. Maybe I will factor out this u. This should not be a horrible idea, and should not be a difficult one to implement. So when you have an expression like this in general, it's just a good idea to proceed. By proceed, we mean investigate and see what you get. So I'm just, investigating. I get something that looks like this. It doesn't look too bad. It's definitely much nicer than this. How do I proceed? It's a good question. So I have a product of two terms in the denominator. That's the first hint. The second hint is that we already discussed how we can deal with expressions of this form. It's something called partial fractions. And it's like magic. It's like it says that you can write this as u and write this as u minus 1. Which is, it's absolute nonsense. Like, how is this even possible, It's very weird. But a and b are constants, and they can be computed. How are they computed? Here's how. So you want to find a, you take the fraction. A is the coefficient of u. So I'll remove u from the fraction, and I'll look at which value of u gives me problems. And in this case it's 0, because if I divide by 0 I get problems. Now don't ask me why this works. This is not the focus of this tutorial. I feel very strict now. Right? You can ask me questions, okay, but just don't ask me now. Well, it's a video. You cannot ask me anyway, so it doesn't matter. I'm just speaking to myself. So, u is equal to 0 is your key value. It's the problematic value. So you take this 0 and you plug it in. You get 1 over 0 minus 1, which is minus 1. Maybe you can try this with b as well. Please pause the video and try it. b is the coefficient of 1 over u minus 1. So I take this thing out. What is the problematic value? It's 1. 1 minus 1 gives me a 0 in the denominator. Then I should plug it in here. I plug it in here, I get 1 over 1, which is 1. So that's amazing, because I can write this as 1 over u, okay, minus 1 over u, plus 1 over u minus 1 du. By the way, please try to also multiply this by u minus 1, multiply this by u minus 1, multiply this by u, and multiply this by u, and see if you get 1 in the numerator and u times u minus 1 in the denominator. You should, because these two expressions I claim to be equivalent. And when you multiply by u minus 1 in the numerator and then in the denominator, then it's fine. It's just multiplying by 1, because u minus 1 cancels out with u minus 1. And same thing for if I multiply by u here and by u there. So this is fine. You can check this yourself. Maybe this will be a proof that this expression works. And partial fractions is just the magic way in which you obtain such expressions. It's not magic, but yeah, here's what it is. So we need to evaluate this, I think much simpler integral. I'll put this in a box because it's not related to what we're doing, in the sense that it's not equal to some integral in here, for example. So this line of integrals it's equal to this. I can actually integrate this immediately. So the negative value you don't need to worry about, I just put it outside. And the derivative of a special function called the ln of x is 1 over x. So that is the antiderivative of 1 over u. It's ln of u. That's an important note to make. It's not ln of u precisely. It's ln of absolute of u. Why is it absolute? Simply because the ln value cannot take, the ln function cannot take negative values. That's number one. And this is a fraction that takes any value. It takes positive values, takes negative values, doesn't take 0. But that's fine because ln is not defined for 0. So that's not something you need to worry about. But you need to worry about negative values. So in order to make this function defined, to extend it to negative values, we just add the absolute one. Similarly here we will have ln of u minus 1. Now do not forget to include the minus 1 that's on this expression. I put the minus here. And this is an indefinite integral, so there's a c. There always has to be a c, as you can see. But I'm not done yet. I'm almost done, but I'm not done. I wanted to recall that u is equal to e to the x. So that's an important note. Now to reach the same expression which is in the notes or in the choices, you would do a very specific thing, and that is the following. So if you are adding two, so this is subtracting two ln functions from each other. I hope that's okay. And by ln laws or rules, if you take away two ln's, you can just write them as one big ln, with the positive ln being on top and the negative one being on the bottom. Of course, this is all plus c. But then we're still not done yet, because our original integral was in terms of e to the x, it wasn't in terms of u. So what was the original value for u? Yeah, exactly, it was e to the x. So it's e to the x in the absolute value. In the denominator, I think it's fine. You don't need to include the absolute value. But it's fine. I just put the absolute value on the whole expression, because why not? And then I add my plus c to conclude the exercise. So this should be the answer for the exercise. Now let's recap what we did. I put it in a nice box. And now I look at what I did. So I make use of this very nice observation. That's number one. And number two, I say, okay, all of my terms are e to the x. Everything is in terms of e to the x. Actually, that's a good hint that you should take u to be is equal to e to the x. But the more obvious hint is that you have a composition of functions. You have an outer function, which is the squaring function, and an inner function, which is e to the x. In this case, you should look at it and say, okay, what if I take u to be equal to e to the x? Is the derivative of e to the x in my expression here? By in my expression, I mean, is it in the numerator? Or is it explicitly mentioned? Because if it is explicitly mentioned, then when I take the derivative, it will always cancel out, and then I get something that's much simpler, like this. Then I make a simple factorization, and with my knowledge on partial fractions, I do the partial fraction algorithm. The integral is very simple. If you know the derivative of ln of x, it's a famous derivative, I think. So you don't need to, let's say, for example, derive it from scratch. And then you just simplify using ln properties and plug in the original value for e to the x instead of u. But the key observation also here is to see why you should use partial fractions. And the reason here is because you have two terms multiplied in the denominator. It doesn't look good, but it would look much better if we had u and u minus 1. And indeed, I think this looks very nice. I think it looks very beautiful. I think that is it for this exercise.